Saxon Advanced Algebra, Lesson 88. Oh, I forgot to write the topic. Well, I'm glad I didn't because I don't want to frighten you. I think these are two words that may strike the fear into the hearts of some of you. And I don't want you to have any preconceptions about this lesson because it's much easier than you think. Exponential functions. Functions is a word that a lot of students have now decided they're going to freak out whenever they see it. Please don't. It just means equations. It just means there's two variables in the equations, two or more. Exponents put the fear of God into some students because they think that they're hard. They also associate them with logarithms. Yes, logarithms are involved in this problem, but they're not as complicated as we often think that they are. Students at your level often completely understand exponents, but don't really get logs, still feel shaky on logs. I am here to help address that imbalance. Oh, look, that's better. It's sunny today and I'm getting weird shadows on my book, so I'm trying to work around that. Okay. Another name we're specifically talking about growth and decay functions, and I want to talk just a little bit about them to you. They're very common in science and also in finance. As an accountant, I dealt with exponential functions, so do not be afraid of them. What is happening? The growth of bacteria in biology, or the growth of rabbits, is another one that is very common. I just want to explain to you what they are. We all know that if you start out with 2 rabbits, they will reproduce quickly and skyrocket, because as each 2 bunnies makes 2 more bunnies, makes 2 more bunnies, makes 2 more bunnies, it's more than 2 too, your population will grow faster and faster and faster, right? This is what we call exponential growth. It's common in biology. It's common in engineering. It's common in finance. And it was exactly what we saw in the COVID epidemic. And we'll still continue to see if we're not careful. Because what happens is that people are slowly passing the disease, but then as more and more people get the disease and pass it on to more and more people, the number of cases and the number of deaths skyrockets. It starts to grow at what we call an exponential rate, which means it's more than just reproducing at the same rate. The rate of growth is getting way faster, okay? So it doesn't always go up at the same angle. Some curves are a little flatter, some are a little higher. We'll see what causes that in a minute. But those are some examples. Biology, it's the bunnies, right? Finance, it's the interest that you either earn or pay on something. Those are just some specific examples. Now, there's also, this is called growth. These are the growth examples, and notice they're all going up. We also can have what are called decay functions. And again, it's time. And this is typically, we're talking about radioactivity, which shows up naturally in certain substances, but over time, the radioactivity will decay. It will break down and go away. And so in those cases, what's happening is that the decay picks up speed and starts to happen faster. Oh, I'm sorry, not like that. Like that. Pretend that's not there. And sometimes it happens faster than other times. Again, that depends on the equation. But it is happening over time. Now, the original amount that we start with is called A You can think of it as a to the 0 for it's at 0 time has passed, or a to the O for original amount. So you can think of that as both a 0 or a letter O. And T always represents the amount of time that is passing. All right. This can also be referred to as the initial value. Different words that mean more or less the same thing. Time is time. It can be measured in days, years, minutes, seconds. It just needs to be consistent, right? Now, that leads us to the equation that we use. The amount of the substance that you have at any point in time is equal to the amount that you had in the beginning times the natural log raised to the power of a constant times the time. So let's just finish filling this in, and then I'll say a few more words about this before we put it to use. Okay, what may be mildly confusing about this is that we have studied exponential functions at least once before, I think twice before, in the Algebra 2 and the Algebra 1 series. But every time John introduces the topic, he gives us a slightly more sophisticated version of this formula, and we are now at the pure, most sophisticated version of it. Before he kind of, I don't want to say dumbed it down, but he kind of dumbed it down for us. So here we are, ready to deal with it in all of its natural glory. Notice that the natural log is very important because it does relate specifically to the kind of growth we experience in these fields. So we would never use the common log. It's the natural log that just describes this behavior. It's kind of like pi. It's just a magical number that bears a special relationship to natural phenomenon, and we just accept it as being a number that describes things, right? We don't have to question that. If you're interested in finding out how that number was derived, I'm sure it's Googleable. But we're not going to get into the philosophy of that. We just know that E is the natural log that describes exponential growth. Just like pi describes the area of a circle. All right, it's just a number that understands something. All right, so what we're going to do is two-step problems, as we have done before, where our first step will be to solve for the constant, and our second step will be to use K to answer the question, whatever that might be. E is not a variable. E stands for the natural log 2.718 blah blah, I don't know, something like that. 2.71. Remember, you can find it on your calculator easily. But this is a variable, this is a variable, this is a variable, and that's a variable. So we will play around with different combinations of given information and then figuring out whatever John wants. All right? Sometimes, depending on which information we're given and which information we want, we have to use logarithms to solve. I hear you all breathing deeply and maybe getting annoyed, but trust me, I'll walk you through it. All right, let's flip the page. Let's rewrite the formula A to the T, A at any given time, equals the original amount times E raised to the power of the constant times the time. Yay. All right, example 88.1. I'm still chuffed about my new notebook. I'm really happy with it. The number of bacteria present at noon was 400. It's bacteria. We don't need to, I mean, is it 400 literal things? Do they weigh 400 pounds? We don't know. It doesn't matter. Now, is noon the beginning time? I don't know yet. So I'm just writing down noon equals 400. And then 9 hours later, 9 p.m., the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. Oops. Okay, now I can start to see the progression. This is the original amount, right? This is the amount after 9 hours, so I put a 9 in for the T, and this is going to be the amount after 24 hours. Okay. Now I kind of get the flow of things here, right? So what I can do, I'm going to sneeze. Excuse me. Now what I can do is I can set this up with all this much information and solve for K, first step. Then I'll try to figure out the answer to this question. So here's my first step. I'm going to solve for K. So I need to know that the amount I had at the end of 9 hours, 800, was equal to the original amount, 400, times E to the K, I don't know what that is yet, and then the time for the first part was 9. Make sense? I'm just filling in what I know into that equation. Now I need to solve for K. Yikes, it's up there. Well, let's do first things first. Let's isolate the base that the variable is attached to. So we'll divide both sides by 400. And I get 2 is equal to E raised, I'm going to rearrange that order. I'm going to write 9K because that feels, K9, that sounds like a dog to me. And Grace is listening in. She's sleeping nearby. All right, so I've got a variable in an exponent that I need to solve, and I know that the way to solve that, which we just studied a couple lessons ago, is I can take the log of both sides. Oh, well, I would like to do that then. Because I see that my base is E, I want to take the natural log of both sides. Okay, now I can use my power rule to take this and jump it down here. So I'm going to just keep writing this. You don't have to necessarily show every step once you get the hang of it. Okay, this I will use a calculator and I will simplify and I will find out that this is equal to 0.0693. Okay, over here what I recognize is that this, what is the exponent that we put on the natural log of E to get E? Oh, that would be 1, right? The natural log of E equals 1, just like the common log of 10 equals 1. Those are like little identity statements that we can use. Now, I can just drop that from this side of the equation, right? 9K, right? That's what taking the log of it did for me. This I had to do on the calculator. Right, to get that the natural log of 2 is 0.693. All right, and now I'm just ready to divide both sides by 9. And I will get that K, you can use a calculator for that too. K equals 0.77. 0.077. I don't think I said that right. Yay. Great. Fabulous. Now we're ready to set up the second part. And what is it that we want to find? John has asked us to find out how much bacteria we'll have at noon the next day. So we are supposed to find the amount after 24 hours. Okay, well, we know that the amount after 24 hours, I'm going to use this, is going to be equal to the original amount, which was 400. And we're going to raise that to the power of E. And it'll be K, which we found was 0.077, times T, which we know is 24, because it's at noon the next day. Yay! This is the easy kind of problem, because look, all we have to do is simplify this monstrous creation, right? Which is a lot, but we have a calculator to help us. So the first step is we multiply these two together on the calculator. Then we use the E to the X button and find the value of E raised to that power. Then we multiply it by 400, and our answer should be, and I did this before I turned my calculator into a camera, 2539, and then you can just write a word, bacteria. Yay. Okay? So in this case, the equation's a little crazy, but we set it up, we solved for K, and we used logarithms right here because at this point we had an equation with a variable in the exponent, and we can't live with that. So we took the natural log of both sides. We knew to use the natural log because the base is E. If it would have been a base of 10, we would have used the common log of both sides. We used a calculator to find the value of the natural log of 2. We took this identity and simplified, and then we just used basic algebra to solve for K. And then we plugged in over here, and we used our calculators to simplify that. Yay, that's our answer, and it's correct. Okay, let's try another one. Oh, John says to sketch it. Okay, this is all he wants, you guys. I'll put it up here. He wants us to write time, and we can just do T. And then he wants us to write the amount, and we can just write it like that. And he wants us to recognize that we started with 400 and that it grew. That's all he wants from us. Isn't that so cute and easy? Right? That's our sketch. Beautiful. Okay. Let's flip. Oh, you guys, my battery is low. I'm going to end this video, go get my charger, and then restart. So hang on and look for part 2. Thanks, bye.